Everyone. This is a repeat presentation of my earlier talk today about H2O deep learning. Who has seen that talk? So if you're here, then you're here because you want to hear more. I probably can add a little bit of extra tidbits here and there. I'll try not to be 100% repetitive so that those who are watching the video recording as well are not getting the same thing twice. I'll try to show it from a slightly different angle this time, mostly from Flow and from Python if you want. So before we get there, first, deep learning is trending, right? You know that deep learning is a powerful method. It's pretty much all you need to know. It works in the real world because it makes representation of the underlying nature of the data that's nonlinear and is hierarchical. So you have multiple stages of nonlinearities, and somehow you can learn more by doing that. It's not just a linear model. It's not just cutting up space. It's making nonlinear transformations of your original data, and then these transformed features are again transformed and again and again, and each of these transformations is nonlinear. So it's a very powerful method, and deep learning itself is basically a bunch of numbers. These neurons that you see in this slide here, the little dots there are all neurons. There's input neurons and output neurons, and in the middle there's hidden neurons. And the input neurons get activated by numbers from your data set, and the output is the number that you want to see. So yes, no is a 0, 1, for example, or you want to see the correct house price for your house that is at the prediction target, then you want that number to be a high number, right? Or ideally the most accurate number in terms of what it actually is and what you predict. So in order to get these numbers right, you have to map the input into the output, and that's basically the job of those weights in there, the connections between each layer. Each layer is connected to the next layer with every neuron to every neuron, like a fully connected neural net. And it's feed forward. That means all the neurons in the previous layer affect the next layer, but doesn't go backwards. This is a simple neural network, and that's what we do in H2O. It's very powerful because you still have a lot of parameters. You can turn the knobs on how many layers you want, how many neurons per layer, what kind of nonlinearity. You can add some dropout where you cut some connections and you say this one neuron does not send out any signals at all for this training example. So that the network doesn't actually get used for that one neuron connection there. And that means that the network has to learn to make that prediction without that neuron. So you basically become more stable to noise, or you can generalize better if you can handle this dropout, as they call it. So there's all these new things that come into display, but basically deep learning is still old school. It just works better now because you have faster hardware, and we have a couple of algorithms that help make this stable and robust. Of course, H2O helps greatly with making it enterprise grade, which means it runs on any kind of data, on any kind of hardware, in any kind of environment. Missing values is all good. You don't have to standardize your data. You don't have to set the learning rate. You don't have to initialize the weights. You don't have to worry about many things. It's all automatic. So the strengths of deep learning are manifold. You can actually extract the learned features. So once you have these nonlinear numbers that are sitting in those neuron activation states, if you want, you can just say, okay, what are they? And just extract them and make a new frame out of those numbers. And then you have your dimensionality reduction that's nonlinear. So this is a generalized version of PCA, if you want, that takes categoricals, numericals, anything, turns it into a lower dimensional, richer data set. So you could even use this method with a small set of neurons to reduce your dimensionality on a big data set. And once you have a smaller one, then you train another deep learning model much longer, for example. And you don't need to do the initial feature reduction. You can do this one time only. Even an approximate version of this would be kind of useful. So there's a lot of ideas that you can put into practice by playing with these models. But the main idea is that it's a simple model, but it becomes complex very fast because there's millions and millions of these connections, and you don't know what they are. They're just trained, and they're trained by backpropagation. That means every time there's an example that comes in, a training example, a row, if you want, in your data set, it makes a prediction with whatever those weights are. In the beginning, the weights are random, and later they get better and better, but whatever the weights are, they get propagated through. The number that comes out is slightly wrong, and you make the correction. And whatever the correction needs to be, that delta gets applied on the entire network. All the weights get modified such that they are better next time around. And you do this modification with a learning rate. You don't do the full correction, you do a percentage of that correction. And that percentage is roughly around 1% or something. But it can be 30%, it can be 0.01% of the actual correction, depends. And this learning rate historically was given by hand. Somebody had to set the value, and that's what it was. Now there are schemes that do this automatically. So every single weight in the entire network gets trained automatically with the right learning rate at the time of training. So it's pretty smart. And since this is an iterative process that just gets better and better, just like your baby's brain or your dog's brain or your own brain, hopefully, you're on the path up, right? You're not going down. So your brain just gets better the more you expose it to French, let's say. And the deep learning model is the same thing. The more French it sees, the better it gets at French. So now the question is, are you done or not? Well, you don't have to know. You can just keep training. You can save it. You can load it back, and you can continue training another day on new data. Maybe you get better French, different French, whatever it is, right? So the same ideas of a human brain apply here. You just learn, and when you're done with French, you can give it a little bit more Spanish, and suddenly it will learn Spanish. So you can distort kind of the nature of the model by training it with new data. And since it's a online learning method, this works just out of the box. It's a great ensemble member because it's slightly different than cutting up the space like a GPM or random forest or a GLM that does a linear model. So you can blend these three models together, or you can even use stacking, as you heard from Erin today. You can use a super learner that you take the predictions of all these models and you train another model that says how to combine these predictions. And that's then the best stacked approach, so to speak. And of course, you can drive these to extremes, but in general, deep learning itself is a pretty good method. It's not the best method for everything. It has its weaknesses, right? It takes a while to train. It's not very interpretable. You don't know what's going on if it's bad. You just look at all these numbers and you see nothing, right? It's a bunch of numbers. So why is it bad? You don't know. You have to try something else. You have to do your own hyperparameter tuning. You have to develop an intuition. So the more neurons in the first layer, the more resolution you get. The more neurons you have in the later levels or layers, the more nonlinear features you allow the system to come up with. And the more layers you have, the more nonlinear this whole features hierarchy becomes. So you can learn really weird expressions. But often a 2 or 3 layer neural net is pretty good. 3 layers of 500 neurons, for example, is going to be good enough for most use cases, as long as you have enough regularization. Because these 500 neurons on each layer, they connect with the other layer. So you have 500 square weights here, and you have 500 square weights here. Together, that's a lot of weights. So that's 500,000 weights or so. And putting that together, if you train all the weights just right, you will probably be able to overfit on your training data without being good at generalizing to the test data. So you have to add generalization, improving things. And that's L1 penalty, L2 penalty, dropout, this kind of stuff. We also have the ability, of course, to impute missing values automatically here because we just set them to the mean. That's what deep learning does right now. It's kind of a way to handle the noise that comes from the data itself. If there's something missing, you just ignore it and take the mean. But there's better methods, as you heard earlier. GLRM, you can make your own missing value imputation scheme based on the whole data set, not just one column. And Angie explained that earlier. So there's a lot of things you can put together, but deep learning itself is pretty powerful. In H2O, deep learning is parallelized. It's multi-node, multi-thread. Everything is pretty fast. You can just throw in any junk data you have and say go, and it should just run. It should never die for any reason, other than if you maybe give 100,000 zip codes or something and say expand them automatically. That's the default, right? It just takes the zip codes that are strings, let's say. They're different categories. They're not actual numbers. And they will expand them into each one becomes a dummy column, a dummy input neuron. And if you have 50,000 input neurons, each one is either 0 or 1, imagine that's going to be very expensive. So right now the model might say, sorry, it's too many, it won't work. but it should never crash. No matter what you do, it should always run. And once the model is built, you can stop at any time. You don't have to wait until the end. You will get a model, and you will also get a Java scoring engine version of that model. So you get plain Java source code. And I want to show you that very soon, so we can look at that. So this time we'll focus on the scoring logic. I want to show you flow, and I want to show you maybe some kind of regression model that we didn't look at in the morning to show you that we have Laplace, Poisson, Tweedy, Gamma, Gaussian, all these distributions. So tomorrow morning, there's going to be an in-depth presentation for half an hour about the top 10 things you should know about deep learning. So make sure to not miss that if you want to learn more. So this is the hands-on tutorial now. Means I will switch to R or Python, but actually I will just launch it in R, and then I will switch to Flow, the graphical user interface. So let's make it a little bigger. So is this big enough? Do you all have a monitor close by? Are you all able to run this, or people are struggling? I hope by now you're able to run this stuff. If not, then please find somebody to help you. There's a couple of helpers around, but otherwise just listen. And you can also look at the files in a directory. So the directory that you need to look at is actually on the memory stick. It's this H2O World memory stick, right, that you copied somewhere, and then H2O World training, and then tutorials on deep learning. In there are all these files, and the file we're looking at is deeplearning.rmd. That's the R markdown version, but you can also just look at the .r file itself. And the HTML version is the printout of the output that happens when you run it. So you can also look at that if you don't have R console up. This doesn't have to be hands-on, but for those that have a laptop and they want to play with it, please go ahead. So I start H2O with h2.init. I delete some of the keys in there in case there were already some in there, but in this case there weren't because we just started the cloud. But if the cloud was restarted again, I can do this here. See, I can just run it again, this H2O init, and it will say, I'm already running. What are you doing here? It's already running. It's been running for 13 seconds. And now if there was any keys in there, I could just delete them again. Okay, so here you can look at the arguments and so on. There's a lot of arguments. You don't need to do this right now, but there's a lot of arguments. So now I will load the data set, set the path, and I'm loading the spiral and the grid data set. Now the spiral data set, if you go look at the, let's open up the web browser. All I need to do is go to localhost :54321. I'm going to make it like this. So when you go to flow, that's just a view into the state of the H2O machine. And you can talk to any single one node that contains the H2O running process. So on a Hadoop cluster, you would have 50 machines that all have this jar running, java-jar, some process. And you can talk to any of them, and they will all show you the same window into the world of H2O. Now you can ask, how many cluster nodes do I have? You can click on admin here. You can see how many nodes are there. Right now it's only one node, right? You can see it has 8 cores, my laptop. You can look at the data, what kinds of data is in here. I have a grid and a spiral. So the spiral data set has 3 columns, X, Y, and a color. Colors are red and black. Each one has 100. The colors don't matter too much. It's a factor column, right? It's an enum. It's not a 0, 1. It's an actual name, 2 different names. And you can look at the distribution of x's, for example. X will be distributed from minus 1.3 to 1.3 something. So that's a distribution of x's. So it's a spiral, and you can do your own math to compute the density of x values on a spiral, right? But this is a noisy spiral, so It's also samples. It's not trivial to compute this shape, but anyway, we just give you a histogram. I can delete these cells. I can look at the data set itself. Simple data. So this is obviously not a big data example, but we have run 100 million rows, no problem. Deep learning runs 1 million rows per second on a cluster of 8 nodes. We've run 100 node clusters. We've run more than 100 node clusters. Some of our customers run on almost 1,000 nodes. So this is just a small data example. I'm now going to run a deep learning model. Here, deep learning model as a model. Select one, deep learning. Training frame is the spiral. And I'm just going to say predict the color. Okay? And I'll say go. At the bottom, I say go. Build model. That's how easy it is to build a deep learning model. And now we already built it. You can click on it and look at it, and you see the AOC is pretty bad. And why is that? Well, the default is only 10 passes over the data. So it only saw 10 times all the 200 black and red dots. And that's not enough to actually learn the spiral. So I'll go up, and I'll change epochs. I can do it two ways. Either I change the field up here in the cell. I change epochs. One epoch is a pass over the data. I can specify 500. And I say go again. And now you can see that it takes a little longer. Still not too long. And I can now look at the model again. And now the AOC is 98.9 on the training data. It just memorized the spiral, basically. And now you want to know how this looks like, so we're going to visualize this in R. But the default is set to 10 deliberately. It used to be historically that we did just small, like we didn't want to run too long, right? Because deep learning runs too long normally. If you have like a big data set, you do 10 passes over 100 gigabytes. You have to process 1 terabyte, and it takes a while to learn these weights and all that. So we just said do only 10. But we just recently added this early stopping criterion, which actually would mean it will stop anyway. You don't need to tell it to stop after 10. You can say do 1 million, but stop if you're done converging. And that's what the new default should be. But I didn't want to mess with everybody's defaults quite yet. But in practice, I always set the epochs to 10,000 and then use early stopping to automatically stop when it converges. So in R, we can now go back and define this function here. This function will plot us some spirals. So I got to open up this window here to show them. Let's hope this looks good enough. We'll make it a little smaller here. So now we will run a deep learning model, a GBM, a random forest, and the GLM. And you see how easy it is to run a deep learning model. All it says is h2o.deeplearning. 1 to 2 is the x, the predictors. 3 is the response. And then there's a spiral, that's a data set. And then there's the parameters that you add. So this way didn't work because RStudio doesn't like when the window here is too small. I might have to turn this on here. Try this again. Here we go. So deep learning just learned the spiral. It detected that there's a spiral and it shaped its contours around it. So this is the boundary between red and black. So deep learning learned that there's a shape that looks like a spiral, and it just kind of memorized it, right? This is not holdout performance. This is training overfitting, if you want. But it's still funny to see how it learns it, that this is a spiral. And you see that I had to do 1,000 epochs to get there. Just like you saw earlier in the flow example, that the AOC wasn't quite good with only 10 epochs. So it has to learn, and it gets better over time. So to show you this learning behavior, we'll do another example where we use checkpointing to first train 1, and then 200, and then 500, and so on. We add more epochs, and you see how it evolves. But it's interesting to see random forest and gradient boosting next to random forest, next to deep learning, right? You see that the tree methods just chop up the space, whereas this deep learning has to learn some kind of a nonlinear transformation. And GLM, of course, has no chance with a curve that's in 2D. So here we can now show checkpointing. So I will run a deep learning model, and I say call the first model DL1. And then I continue it, and I say call the next model DL2. But start it from this checkpoint. So the second model actually starts from a checkpoint. So when I run this cell, the first model has one epoch. That's basically as bad as a linear model, because one pass over those 200 black and red dots is not enough to make those weights all correct to learn the spiral. And after 250 epochs, still not that great. 500, still not that great. 750 gets better. With 1,000, it should be good. So this is not what you will see on your laptops, but something similar like that. Everyone that runs it will see something slightly different. Everyone finds a different local minimum in the optimization space, right? This is not just one big hole somewhere in the landscape of optimum where you just drop your ball and it lands on the bottom. This is not a convex problem. This is a highly non-convex problem, but it's still good enough to find something. So now we can look at different sets of neural architectures, if you want. So is it better to have 4 layers of prime numbers, or is it better to have 3 times the 42? Or is it better to have 2 times 200, which is the default? Or is it better to have just one layer that's super sharp? So one super sharp layer is not that great because it doesn't learn the nonlinearities as much, right? It only sees the pixels, but each of these 1,000 neurons sees all the pixel or all the XY values coming in, and there's only 2. So each of these 1,000 has a different detector, if you want, for X and Y. So there's 1,000 feelers for X and Y, and then that's it. Then those 1,000 have to make up the last yes or no answer. And that's not quite enough. You want to have multiple layers to really contort the space and say X squared plus Y squared has to be growing with like this angle or something. This is not a trivial formula to memorize. So you have to kind of have more nonlinearity. So 2 layers gets you there. Actually, the 4 layers of prime numbers looks pretty good up there, right? For the fact that there's only 11 numbers and 13 numbers in each layer. So that's a pretty good model. So you can see the power of deeper networks. Let's look at different activation functions. So I said earlier we need a nonlinearity to make that mapping from numbers to that I get into my, if I'm the neuron, I get these numbers in and then I spit out a new number. And that new number is a nonlinear transformation of the numbers that I collected, if you want. The sum of all the incoming weights comes into me, that's one number, and then I transform that. And the 10H is a sigmoid. It's something that goes up like a soft step, whereas the rectifier is a sharp edge, if you want, but it's flatlining on the left. So anything negative stays 0, and anything positive, X is X, which means the rectifier is the easiest to compute nonlinearity. It's just the max of 0 and X. That's your output. And that's so cheap to compute that it's actually worth doing it over and over again, and you get sharper cuts in your space by having all these 0x, these sharp corners in your function space. You have a lot of these sharp corners. You can stitch them together, and you can approximate any smooth function with that. So the rectifier is pretty efficient, as you can see. They all had the same number of epochs. The rectifier with dropout is actually the worst, but it doesn't mean that it's the worst for real use cases, because this just meant that it did this regularization that I mentioned earlier. It didn't see all the connections at all times, so the network kind of was forced to cope with a loss of information. So it was trained slower than it could have been trained. Half of the information of the French I spoke to you didn't listen to. You closed half your ears, right? At random times, you closed your ears. So how are you supposed to learn French that way? But if you do it over and over again, it actually gets better, because you don't have to be perfect at listening. You get it just like by listen half the time. So we could do the same thing with more epochs just for fun. Let me just do that. But you'll see that the first one, the 10H, is pretty slow. So generally I don't do that. But now you can go to flow, and you say what models are being built. You can go to the jobs here, and you can see done. One of them is saying running. You can look at that model. You see how fast it's training. And you can also look at it. This is the number 114. So if you go to list all models, there's somewhere a number 114, right? But it's alphabetical here, so I have to find it. And it's already pretty good. You can see the history here. This is the mean square error over time. You see it gets better. If you wonder what's going on here, you can look at the values. You can get the POJO. I mentioned I wanted to show you the POJO. Remember, this is the actual Java code. This is the scoring code. This fills the two standardization coefficients for the scaling and the offset. These are the neurons in each layer. 2 input, 2 outputs, and then 100, 100. And then you actually will see the actual code. This is the for loop here that does the matrix vector multiplication, partial sums unrolled, and you get the activations that are here. This is the sigmoid function, scaled and shifted, which is called hyperbolic tangent. It's just the same as a sigmoid, but from -1 to 1. It's symmetric around 0. So this is the whole math. You can look at it and you'll understand how this model works. Except that you don't know where these numbers came from. At the bottom there will be all these numbers here. These are the numbers of the model. And you never know how this happened, right? It just is like that. So that's the nature of the deep learning model. It's a black box. So now you can see that the rectifier with activation, the rectifier with dropout after 5,000 epochs still didn't get quite everything right, because 50% dropout, which is the default value, is just too much. So there's 100 and 100 neurons in each layer, and half of them didn't see anything for each example. So we only saw 50 random ones. And it seems that it's just not smart enough to learn with only half the information, because this X and Y that's coming in, that's good information, right? It's correct. It's a little bit noisy, but it's still, you want to see as much as you can. So there was no input dropout, so you got all the X and Y values, but then you make features in your first hidden layer, those weights that create those new features, and then you just omit half of them. So it's a waste to throw away half of your features that you just learned just because you want to generalize a little better. It seems like it's not good enough. So either you can try more epochs, or you can reduce the hidden dropout ratios to maybe 0.1, 0.2, and that might give you a better model. But in this case, of course, the only goal was to remember the training data. So I think we should look at a little bit of the COF type data set as well. This is a different data set. Did you all see a COF type example earlier? Cover type, either GLM or GBM. They both presented this data set. So this is a tree cover type. Let's look at it in flow. So there's a lot of here, train. So there's a lot of features here that have to do with map data. So there's elevation aspect of the I think it's the slope of the landscape or something. Let me close this. Then there's a hill shade at 9 o'clock, hill shade at noon, hill shade at 3 p.m., wilderness area, soil type, cover type, all kinds of stuff. We want to predict the cover type. So if you look here, there's 7 classes of cover type. It's either this tree or this tree or this tree or so on, and most of them are class 1 and 2. So the challenge will be to find which one it is out of those 2. If you get those right, you're basically done with the data set, right? Most of the time, that's all you need. The rest is just small noise if you want. Of course, you can get those right too, but let's see how it looks like. So if I go back into R, I just loaded the data and I split it 3 ways, 60, 20, 20. You only need to specify the fraction here that's not adding up to 1. Let me go back. Oh, I'm sorry. Okay, so here we are. So when you do split frame, you say 60-20. It knows that the other 20 are going to be the third holdout set. You don't specify all 3 because they add up to 1, right? So I did that. And now we have another way here to do some plots. We can actually plot a, sorry, I need to open this window again. RStudio is not letting me get away with it. hope you can do it in your windows more efficiently than me. Okay, so I plotted it. Here we go. So this plotted elevation versus cover type. And you can see that the cover types 1 and 2, the bottom, class 1, class 2, I apologize, the font is a little small. The bottom two are classes 1 and 2. They're at these elevations. And the elevations go from like 1,800 feet all the way to 3,800 feet. And this is a scalable way to plot big data. That's what just happened here. So if this data set had been 500 gigabytes on a cluster of 50 nodes, you could still have called the same method that's called h2tabulate. It would have cut up the space into bins. And even that works for categoricals, right? Like the 7 classes, there are 7 bins. And we would just count how many are in each, and we would then return those aggregation counts back to the user as a small little table of 7 times 20 or something, whatever it is here, 7 times 30 or so. So that's a small data problem for R to handle. R can plot that, no problem. And the cluster can compute those numbers because we have a parallel map reduced that just counts up stuff as it passes over it locally. So this is a cool way to see what's happening. And I can plot other stuff. And you can see that this is, for example, the elevation versus the horizontal distance to roadways. You get this scatter plot. And I'm sure that you'll find this informative if you look at your data sets in practice. So this is a nice little thing to know that you can do this stuff as well with H2O. So now let's set the response to be the cover type and the predictors to be everything else. So the predictors are all these here. Elevation, slope, and so on. And now we'll just run a deep learning model. And I will run it all defaults, except that I only do one pass over the data. That's why I say epochs equals 1. And I say variable importances is true. So I want to see the variable importances. And now that it's running, I can go back to flow to inspect the model. So I can go here, list all models. And this will probably be called something first. Yep. And now you can see the model. Let me get rid of this here. So the model has confusion matrices and a convergence plot, and here the variable importances. So you can see that the elevation, for example, shows up high. And the validation accuracy is 20% error, so 80% right out of those 7 different classes. So it's not too bad, but also not so great. If you remember, random forests can get to 5% or so, and this is at 20%. But we only just did barely one pass or so. If you look at how many passes we did over the data, we did 0.7 epochs at the time I was loading this. I can load it again. Now the variable importances have changed a little bit. The model has converged a little better, but we're still stopping right here at 1 epoch. And we're still at 18%, so it's not the best model. So now we can go back. We can look at the variable importances from R, by the way, as well. You can just get that data as a frame into R, and you can just look at the variable importance table, which is small data. So as data frame actually pulls it into R. It copies it from the cluster to R. All the other processing happened only on the cluster. In this case, it's my laptop, of course, which is my one-node cluster. But in reality, you will never run on your laptop unless you do small data. So one cool thing I mentioned earlier is this early stopping. So I said I will always use like a big number for epoch, something like 1 million, because I don't care. I just want it to be big enough so I can finish based on a convergence criterion and not based on the number of epochs I had to guess when I started the model. So now it's running. It's doing 3 layers of 32 neurons. So this is faster than the other one because the other one before us, 200, right, was a bigger neural net. This is a smaller neural net, so it runs faster. But since I said 1 million epochs, your progress bar is going to take a while to get to 1%, right? It will take 10,000 epochs to get to 1%. So you'll never see the progress bar move right now. So maybe you shouldn't specify 1 million epochs, just specify 100 or so to see the progress bar. But actually, we can still go to flow. I will look at the list of models again. This is the faster one. You see the convergence here. And as soon as it flatlines the orange curve here, the validation error, this should stop. Because I said, when I trained the model, I said after 2 repeated scoring events that don't improve by at least 1%, the 0.01, in misclassification, stop. And it just stopped, right? You just saw here, this came back. And the error now here, the misclassification error, is 14%. So it got a better model by doing something quick and dirty. You can see here it converged, flatlined, and it stopped. You didn't have to know that it was at 28 epochs or so. So this is all automatic. And now we're at 14%, so a significant improvement, and it didn't take that long to run on my laptop. And this is, after all, still a data set with 500,000 rows. And it has categoricals in it. There's 44 categorical factors, which expand the number of neurons to more than the 12 columns or so that the data set has. If you look at the data set itself, it didn't have that many columns, but here it says 56 input neurons, right? So that's the horizontalization, as we call it, the one-hot encoding, the dummy variables that get made that say, if you are this type or this type, soil type or something, then you're either 0 or a 1 for those soil types. And so it makes extra columns, but you never actually see them in the frame. The frame itself, the data set that you have in H2O, doesn't have those columns. Only H2O deep learning makes those extra numbers up per row. It never materializes them. It just sets the input neurons to be the 56 predictor values. So each column is either a predictor or it can be many predictors if you want. If it's a categorical column, it can be many, many predictors. It's either red, green, or blue, or this soil type or that soil type. So columns doesn't translate to input neurons, but features, if you want, like actual levels of categoricals plus the numericals together, that gives you the number of input neurons. All right, so now you wonder, can you do better than this? Well, you saw that this was all automatic. There's not much going on, right? All I did was I specified X, Y, predictor response, and some hidden layer configuration, and I said run forever. I also said validation sample should be 10,000, so my sampling for scoring is going to make it faster here. I don't want to score on the whole validation set. So now we can run it again, a tuned model, a little better. In while it runs, I'll show you a couple of these examples of these parameters. So this is 3 layers of 128. So it's a smarter neural net, if you want. Smarter because it has more neurons in each layer. It also has the learning rate set manually. So if you look at rate down there, it says 0.01, I mean. That means the learning rate is no longer adaptive. I said adaptive rate equals false. This is hand-tuning the learning rate, old school neural nets. And I'm saying there's an annealing, which means the learning rate slows down. It goes even lower than 0.01. Every 500,000 rows, your learning rate goes down by half. So this is that annealing. And then there's a momentum, so it starts at 0.2 and it goes up to 0.4 over 10 million rows. And that's just a tuning parameter. The momentum is between 0 and 1. It's a relative kind of speed term that says if you're correcting this weight in this direction, then next time you should still go in this direction. Just keep pulling the same way. If you have a long valley, you shoot along that valley much faster. That valley is optimization space valley, right? So it's not easy to know whether that's actually a valley or not, or is it a saddle point, or is it some weird punched holes in the ground. But typically you will have valleys sometimes, and this momentum will just follow this valley like a river, much faster than a single person walking slowly. And this is what momentum does. And the L1 and L2 are just regularization terms, just like in a GLM. And now this model got us to 8%, so much, much better. And I'll show you this, and then we finish. So the tuned model, see, converges faster. And this was only 10 epochs. So I was able, in 10 epochs, to get you to 8% accuracy faster than the other models. And you can see here the confusion matrix is pretty good. So basically it means don't give up tuning. If you think deep learning is not performing well, most likely you haven't tuned it right. Of course, that's my excuse to say it's your fault. but in reality, it's possible to get a lot out of deep learning models because they're so complex. You can do anything you want with them. But it's not always the best tool. So keep in mind, it's a great ensemble member. You can use GBM. If you have only one shot, GBM will be fine. But if you want to spice it up a little and run another model, then deep learning is a great candidate. So thank you very much, and see you tomorrow at 11. Do we have room for questions?
There's nobody after you. So it's as patient as folks are. We can probably put in 10 minutes of questions if folks want. We've got one back here already. Enough deep, we got a couple up here. Well, go ahead and I'll bring the mic around.
So my question is, what is actually the difference between a deep learning and an old-fashioned multi-layer feed-forward network with backpropagation, which was actually developed in the 80s, right?
Correct. So Schmidt-Huber and other people have done this stuff long ago, right? Long time ago. There's not much new. There's Dropout is new. A couple of concepts like the leaky rectifiers, maybe the renormalization. There's this parameter called max W2, which says then if the sum of incoming weights squared is more than this certain parameter, then don't let it be that big. Just scale it down a little bit to max it at this level that you specify. So there's a couple of tuning tricks, that algorithmic advances, if you want, that make this stable. The adaptive learning rate is something that came out recently, 2012. So there's things that just make these old school neural nets work better, but they're not really different. They just now work. It's like a car that has rubber tires instead of steel or wooden tires, right? It's the same kind of technique. It's just refined.
Yeah.
Oh,
I don't. The follow-up question. So, I mean, you have this annealing parameter there. I mean, that sounds very much like simulated annealing, also from the really old days. Isn't this very similar, where you basically based on?
Yes, you're lowering the temperature, if you want, of the system in some sense, but it's not really, it's not like fermions that are shaking or anything that you slowly freeze in place. It's more like the learning rates, right? So the update to the system is what you're freezing in, not the system itself. So it's related, yeah.
How much can you comment on your focus on stochastic gradient descent optimization? There were other options to consider, right? LBFGS or Hessian-free. Was the focus on SGD about accuracy or about scalability, about both?
Mostly scalability, and LBFGS is typically used for smaller data, as far as I know. You can do conjugate gradient. For small data, you can have stuff that converges much faster and will give you the right answer right away without having to iterate all these epochs. But most people, like even Hinton himself, uses SGD all the time. So I trust the leaders in the field. And it's been shown to be fine. The convergence rate, yes, you see with the manual tuning of the learning rate, you can say adaptive learning rate is not the best thing. So, but it's still easy, right? Every time you say go, you will get a model that typically converges. Whether it converges to the best final value or not is a different question. So, for example, I ran the MNIST data set and I got the world record number without doing convolutional neural nets or anything with the adaptive learning rate. I didn't do any hand tuning at all. And I got to 0.83% on the test set without any feature engineering or rotation or anything. No pre-training, no unsupervised, just regular supervised training and say go, and that was it, a one-liner in R. So it's very powerful. SGD will get you there. Whether it's the fastest way to get there, who knows, but it's very solid and proven.
If you have a large number of hidden layers, say 6 or 7, one of the problems is getting convergence. Do you have any guidance on how to address the convergence? I've heard that initially do an unsupervised training, use the weights from that, and then do a supervised training. How does one even do an unsupervised training?
So there's two answers to your question. The first is, yes, use rectifier with dropout if you want to do many, many layers, because you have a lot of zeros added by either the rectifier or the dropout that both then end up not propagating those gradients over too long a distance, which means the vanishing gradient problem is reduced if you have a rectifier with dropout. So you can get to 6 layers or so. I haven't done 7 myself yet, but I mean, it takes so long to train, usually the benefit is not worth it. Second thing is for unsupervised, which we can also do, you basically have no response, and you tell the system to just learn an identity mapping via compression. So you're saying, let's say in this case, 56 input neurons, and it goes down to, say, 20, 10, 20, and then goes back up to 56. The goal is to learn your input, and at the other side, it should come out again as the same thing, even though you actually compressed it down to 10 neurons. And this unsupervised training will force the system to learn these 10 neuron states well, basically. So it learns to create those features, because every single row that comes in gets compressed from 56 to 10 through 20, and then back out to 20 or so, or 30, whatever. It doesn't matter what the numbers are. It can be anything, as long as it goes down and back up. And in the end, out comes a number for each of the 56 that hopefully matches the input. And that's the unsupervised training. And that you can use as a dimensionality reduction tool, because you now know that the features it learned are the intrinsic features, not to predict anything, just to reconstruct the data. So that's the structure of the data is stuck in there. And if you have many, many layers, then it becomes difficult to train from scratch. Because if you imagine you have 6 layers and you have 56 outputs or 10,000 outputs, it's very difficult to train all that. So what we do there is we do stacked autoencoders. So this reconstruction thing is called autoencoder. And if you do stacked autoencoder, you just do 1 layer at a time. You freeze everything else and you just train 1 layer at a time. And I can point you to an R script that we have in our GitHub that runs as our daily test that does exactly that. So we do layer by layer, and that makes it more stable.
I actually have several. So one thing that's always confused me in the very beginning is that the input nodes actually for you data set is called spiral. So basically you only have a 2 input node, is that right? It's number of features, you are X and Y. Oh, yes. No, there was a red. Oh, red is labeled.
That was a response, yeah.
So this is, okay. And another thing is, you said an autoencoder. Is it available in the H2O already?
Yes. So
is it like the hidden node has to be less than, or you have other constraints or not?
No, it can be anything, actually. You can make an autoencoder that blows up the data and then goes back down to the identity, but that will most likely not lead to very useful features being learned. So I can go to the conf type here. That was the name that the frame got from it, parsed it from R. I can say no response, no none, no anything, and I'll just say autoencoder true somewhere. Here. Now I say go.
Do you have to specify sparsity, something like that?
You can, but the sparsity is only some kind of enforcement to try to get the weights to be sparse, but you don't have to do that. Like the autoencoder right now that I'm running takes 56, 200, 200, back to 56, and it has to learn that mapping. So we can look how successful it is at doing that. So we can look at this guy here, this key, and I can just say, make a new cell here, and I type in here, get model, and put in this key. Now we can look at the preview. You see it learns nothing. It blows up. It's unstable, see? It didn't learn anything because I told it, hey, here's 56 input, make it into 200 through some noisy weights, and then compress it back to 56 to get the same thing back. It's not a good idea to like give it too much work. So what you would do is you would actually try to compress it. So it would be better to do something like 50 alone, let's say, and maybe it would be also better to do a 10H as something smooth, a sigmoid. You don't want to have this sharp step function if you only have 1 layer. Now I'm overriding the same model key. And now I look again. It hasn't trained, hasn't scored yet. Let's see what it does here. Okay, now it's going down. See? Now the training error was 0.09 initially with random weights at 0 epochs, and then later it became almost 0. I don't know exactly how close to 0 it got, but it basically memorized everything, going from 64 to 50 and back to 64. So what it did now, it actually had the response in it, right? I took all the columns. I didn't ignore the response. So because to an autoencoder, it doesn't matter. The response is nothing special. It's all just the same. It's just columns of a data set. So it took all the 64 expanded features. It went down to 50 and back to 64. And those 64 that came out were just identical to the input, even though it had to go through 50. So it basically learned a very efficient compression here. And it's not too hard to imagine, because losing 14 numbers out of these categoricals that are all kind of 0 or 1, there's redundancy in there. So it basically learned that mapping of the categoricals just right here. But this gives you an idea. This is how easy it is to do autoencoders. But you have to be careful to look at the convergence. If it's worse than the initial value, it basically didn't learn anything. It has to converge. It has to get better than the random noise that it starts from.
Basically the way of the feature engineering, or
Yes.
how do we use that into the feature engineering matter?
Well, this is a black box feature engineering, right? So I can now take this model here right now, and I can say predict. And I can say predict on the cuff type, and I can say compute the deep features in hidden layer number 1, or maybe 0. I'm not sure how the indexing. Yeah, it's 0. It's Java indexing. So now it actually predicts the hidden layer number 0, which is these 50 numbers. And now out comes this data set with 50 columns. This is the compression. These are the deep features of the layer 1 of this autoencoder. So these are the 50 numbers that I said are just good enough to represent the 64 numbers, right? So this was the feature engineering. And you can look at, for example, what this one number looks like as a distribution. It's something kind of a Gaussian, but not quite. So this is some feature that has this bimodal distribution that has some intrinsic value to do anything. But you don't know what this is. This has nothing to do with feature 1 in the original data set. This is just some combination of everything in a nonlinear way, right? That's the black box magic of deep learning. It just gives you 50 features that are sufficient to represent the 64. Yes?
Okay. Another question I have, H2O, it has to be on the Spark, or it can be
Can be anywhere, yes. So it's Java, which means you can take 10 ARM chips or something from your little kid's toy computer and make your own cluster, or you can take a supercomputer with 1,000 Cray nodes, or you can take a Hadoop cluster or a Spark cluster, or 12 laptops, my Mac, your Windows, doesn't matter. They can cluster up. So basically, anything will work. Obviously, in practice, you want to have 20 or 10 or 50 machines of the same kind, same memory. You want to have a lot of memory, ideally 200 gigs per node or so. You want to have 32 cores. You want to have beefy servers to do machine learning. But in theory, anything goes that runs Java.
So basically, if our data is on the Hadoop, it should be the Hadoop cluster.
Yes, perfect. Then it has the same data on the same locality, right? You want to benefit from the HDFS being stored on your compute nodes. So when you say import these 100 gigabytes, every node will say, okay, I'm reading my 10 gigabytes. Then those 10 gigabytes should come from somewhere nearby on the same rack, same system. You don't want to send it over the VPN to your home machine or something.
There's another one case related to the feature engineering. As long as you have all the data, all the potential feature listed, like 1 billion, so you can do this. What happens if, probably there's no answer. If there's no data we forget to include it, then it will not be ended there, is that right?
Yes, that's why it's important to do like baseline studies, right? You want to see, with this data, what can a GBM do? What can a random forest do? What can a GLM do? And then you do your deep learning and see if you can beat them. But you don't want to just blindly guess and just say, oh, 60% is all I can do. You have no idea why. You want to do maybe some simple statistics too, right? We can compute the mean and predict that and see if that works. You basically have to know what you're doing in every case of data science.
Thank you.
With the autoencoders, is there a parameter for noise injection or corruption of the input data?
Yes, you can do input and hidden dropout, for example, to add noise, right? That would be one easy way.
With the input dropout, are you setting the values to 0?
The input dropout by default is set to 0. If you set 0.2, for example, then 20% random inputs will be dropped for every input, for every row of the data, but you don't know which ones, it's just random. But dropout in general is always per row. Every row that comes in has a different set of input neurons disabled or hidden neurons disabled. And you can set the rate from 0 to 1 for the input layer or for all the hidden layers connecting the other neurons. So it's always specifiable by the user. What's the rate of dropout?
So what last one?
I have a question regarding the grid search and tenfold cross-validation. So when you do grid search and tenfold cross-validation on data and it returns like a model, the best model it returns, is it based on the AUC or it's based on the AUC?
No, it's based on anything you want. So when you do grid search, you just get a list of models back right now. We don't tell you which one is the best. You can do a loop in R or Python. In Python, I think there's some helper function that's already shipped with H2 that shows you that you can sort by any metric. N-fold cross-validation will not optimize anything except when you do early stopping. So normally N-fold cross-validation just tells you how good your model is on internal validation, even though you train it on all the data. So you train one model on all the data, and then you train N more models on the holdout splits, and they are just made to tell you how good your main model was, right? It's just meant to validate it.
Yeah, so it's the tenfold cross-validation AUC for each one.
Yes, you get a train and validation metric for each, but that's not actually what's used. What we do is each one of those n-fold models takes the nth holdout and makes predictions for it. And then we stitch together those predictions, and then we say, oh, well, how well does this do against the actuals for the full training set? And that gives you one new AUC metric, as if you had a regular model that you just score the training set with. That's how we get you the AUC for the n-fold. Now, when you do early stopping, there's a difference. If you do early stopping with n-fold, then all the n models, the fold models, will stop early at different places, and then you take the average stopping point in epochs, or in trees for GBM or random forest. You'll take the average stopping point and tell the main model to run with that. So you get actually a better model than just the cross-validated one. You get a tuned model, but it's tuned on internal holdout data. So it's not cheating. You're just basically getting the best model you can for the number of epochs. So you basically auto-tune the number of epochs automatically. But then the model you're getting back was trained on all the data, and it didn't cheat in any way. You basically didn't have to tune the parameter epochs.
Okay, thank you.
So it's very nice to run early stopping in n-fold cross-validation, and grid search over that you can do as well.
All right. Well, let's all thank Arno for his
All right, thank you.